Now I'm not going to talk to you about modular arithmetic for a moment. I'm going to talk to you about what is abstraction. Do you know?
Um, Taking out bits, so there's just like one problem to solve.
Sorry, say that again.
Well, in computing, it's like taking parts away from the problem that are don't need to be solved. So you just got the main problem.
Okay. Uh, Take, do you have help?
Not sure.
Okay. Let me tell you something that we do since we are very, very young. Okay, but because when we are toddlers, somehow we learn that all these things are, what are they?
Dogs.
Okay, so we learn the concept of dog, and we learn to recognize even from drawings. So I mean, well, animals within the park. So when we have, if we have at home, okay. So the concept of dog is more abstract than the particular dogs. Okay, later we learn another concept. We learn to recognize that what's common among all these.
Three.
Hmm?
There's three of them.
Yes, exactly. We learn the concept of number three. I mean, and three is more abstract than all of these because you can see one day three dogs walking down the street, but you will never see number three walking down the street. Later, when we learn other things at school, we go from numbers to what? To letters. When we learn some algebra, okay? So this is more abstract than the numbers. So you see, it's like a ladder of abstraction. I mean, we start with concrete things, then we go to concepts like dog, apples, cats. And then maybe when we start adding, we start saying 3 apples plus 2 apples is 5 apples. But at some point we drop the apples and we just say 3 plus 2 is 5. And then at some point we go from adding numbers to adding letters. So so what do you think? These are particular cases of what? I mean, what's the abstract concept here? It's modulo n. Okay, and the way they taught me, I think that was a uni. They gave me the definition, and then they say, "Oh, these are examples." I think actually it's more natural for humans to see first the particular cases, and from the particular cases, create the abstraction, the abstract concept. Okay. So, what do you think is? I mean, what is mathematics about? I mean, what does is the mathematics study?
Finding what
Okay, Take first.
finding what's equal to what else.
Sophie?
The study of numbers and letters.
Okay, numbers, letter, but well, letters in general, that could be language, but well, some people say answers like numbers, figures, okay, because there is geometry. But it's not about, it's about finding patterns, generalization, abstraction, which I think in a sense, Take wanted to express that when he said what is equal to what. I mean, like going more and more abstract, okay? Now, like 10 years ago when I started giving this, Wikipedia used to have this definition. Okay, I think they have changed it now, but at the time, well, with that definition, it was for me very interesting that the first word was the abstract study of all this. Okay, and that's I think what makes fascinating mathematics because you have learned these concepts, area, volume, probability, and if you study pure math, you will learn a beautiful theory called measure theory. And what makes mathematics so powerful in practice is that you can apply abstract mathematical models to different sciences. Okay, so well, sometimes more abstract is more useful. I say sometimes because, well, maybe abstract art is not necessarily useful, but in terms of mathematics, many times it has happened that models found in physics then were applied to economics, for example. Okay, and modular arithmetic has a variety of applications: cryptography, music, video games. Can you think of an example of a video game that uses modular arithmetic? There is an old-fashioned one popular in the 80s, but maybe you know it. Does any of you know Pac-Man?
Oh, how is that modular arithmetic?
Do you remember that when is it like a little ghost goes outside the screen, what happens?
Oh, it comes back in on the other side.
Yeah, exactly. If it goes out on the right, it appears on the left. And if it goes down, if it disappears down in the screen, appears on the up. So what they are doing there, let's say the pixels, you know the concept of pixel in the screen?
Yeah.
Okay.
Yeah.
So let's say the size of the screen is m times n. So there are m pixels in the length and n pixels in the height. So what they are doing with the coordinates of the little ghost is they are computing the coordinates modulo m horizontally and modulo n vertically. That's why, so when it disappears on the right, instead of going to n plus 1, it goes to 1 on the other side. You see? You follow?
Yeah.
Okay,
Yeah.
so that's one application. Now, something great about abstraction is that it allows to unify concepts. For example, before these sessions, I mean, you knew how to add hours, you knew how to add even and odds, and you knew the last digit arithmetic, because when I asked you those questions, you knew how to answer that. But you had not realized that all of them were particular cases of something more abstract. Okay, so in this case, abstraction has helped unification, and well, it was Gauss back like 220 years ago that defined this in this book. Okay, and there is a long history of abstraction helping unification. Let me quickly give you examples in physics. Ever since Aristotle, at least, we used to think that physics on Earth, where things tend to go to the center of the planet, was different than physics in heaven, where things float. Okay, and then Galileo studied that, and Kepler that, and you know who unified these two physics? It was Newton with his universal law of gravitation in his Principia in 1687. And for that, he created calculus, okay? Oh, wow, I had forgotten that I also had this here. I put so much stuff here. So, well, do you know how to see that the moon is falling just like an apple?
No.
No? Okay, I will have to, okay. Imagine, sorry, I think I have this in slides, but okay, imagine that is Earth, okay? And imagine that there is a very tall tower and you are at the top. If you were to throw an apple, let's say to the right, it would fall something like this, no?
Yeah.
Yeah.
Okay. If you throw it harder, well, that is already, I mean, that is already very hard given the size of the planet. No, I mean, the usual thing would be something like this. No, okay, but let's say you are throwing it horizontally. Okay, So if you throw it stronger, it will fall like that. And if you throw it even stronger, it will fall like that. But there is, and maybe like that. You see where I'm going?
Yeah.
There is a force which you could use to throw it, so that would make it fall, but the curve of the fall will match the curve of the Earth. And that will be a satellite, an artificial satellite. And that's what's happening with the moon. The moon is constantly falling to the Earth. It's just that the curvature of the fall matches the curvature of the Earth. And then we're lucky it doesn't crash. So that's one of the big achievements of Newton, to realize that the same force that makes the apple fall is the same force that makes the moon go around. So it's the same physics in both. Okay. Well, later, do you know who unified these two? Well, probably it's Maxwell with electromagnetism, his Maxwell laws. And do you know about this? Nobody has unified those. Okay, but what I can tell you. Well, and Maxwell used very abstract mathematical tools, and I'm sure that if anyone succeeds in unifying these two, it will be using very abstract mathematics. Okay, maybe one of you will do it. Okay, so notice I haven't defined formally abstraction. What I have done is given you examples, and then you have created the concept of abstraction.